All right, cool. Hopefully everyone can see that. Thanks, Luca, for having me. Thanks everyone for coming today. Yeah, I'm Jeff Boeing. I am an associate professor. Old habits die hard. I'm an associate professor at the University of Southern California's Department of Urban Planning and Spatial Analysis. I'm on sabbatical right now in Europe for a few months. The the good news, but I guess the bad news is that when I get back to the US, I'm also going to be the department chair. So this is my last hurrah for fun before the real work starts. I also direct USC's Urban Data Lab. I'm a non-resident senior fellow at the Brookings Institution. And today, I want to talk about some ongoing work in progress that I have been working on for the past few months. In particular, in as much as I'm a relatively new associate professor, I got tenure almost a year ago. And the first big thing I've been doing post tenure, where I've been really trying to just find something that I find interesting for the first time, like a real passion project, instead of thinking about university expectations. So, what I want to talk about today is this idea of there being universal patterns that exist in urban form, and in particular, street network form. So, I will make this argument that we can measure street networks and find certain convergence to a set of universal patterns that we see everywhere in the world. To put it another way, my argument is going to be that cities are much more similar to each other than I might have necessarily thought going into this work. So I'm going to start off thinking about this classic question of city is not a tree. I'll unpack what that means, and then shift from that to thinking about the traditional focus on urban heterogeneity. So most of our work in urban science is about how places differ from each other and how we can use those differences to explain interesting outcomes in urban living. From that, I'll propose this hypothesis of there being certain universality in the form of street networks. I'll show you some findings around that, and then theorize it through a set of fundamental constraints that planners face that both, I think, can explain the emergence and convergence around these patterns, but also present some interesting constraints on what we do in urban practice. Okay, so with no further ado, start this off. A city is not a tree. So if you don't recognize that phrase, it comes from a provocatively titled paper from 1965 by the British American architect and planner Christopher Alexander, who made this interesting argument around cities and trees. So basically, he argued that urban planners tend to see cities as trees. So these hierarchical, top-down structures. When in reality, he claimed cities are actually semi-lattices. So successful, naturally evolved cities are semi-lattices rather than these hierarchical, rigid structures. Now, Alexander's paper was really influential. It shaped a lot of thought in urban design, urban planning, urban geography, but also in complex network science as it emerged over the coming half century. But Alexander sort of metaphorically gestured at mathematical formalisms around trees and what trees are, borrowing kind of metaphorically from some of the underlying mathematics of what treeness is. So what I was interested in for the first part of this study was thinking about treeness more formally and trying to measure to what extent cities are or are not tree-like. And the way that I am doing that here is by looking at the minimum spanning tree. So for those unfamiliar with it, the minimum spanning tree comes from graph theory. The minimum spanning tree specifically is the minimal amount of network needed to connect all of the nodes in the network. So it's a fully connected graph without any cycles in it. In other words, there's zero redundancy. And what we can do is we can take that minimum tree, compare it to the full network, and see to what extent the full network diverges from it. So how close it is to that minimal spanning tree. And what those trees look like is something like this. So in this figure, we can see two different kinds of street networks in the top versus the bottom row. So the bottom row is pretty tree-like. In white, we see the minimum spanning tree of each network, and in red, we see those excess links that exist in the real world that are above and beyond that minimum spanning tree. So in the bottom, you see very few. There's just a handful of extra links in each city, but the city's full network very closely approximates its minimum spanning tree. On the top row, you instead see cities with a lot of redundancy. So they're very different from their minimum spanning trees. That is, these grid-like networks on the top row have a lot of extra links. There's a lot of extra stuff in them beyond the minimum necessary to be able to get across the full network. So the top shows lots of redundancy and low treeness. The bottom shows very low redundancy and high treeness. And we can measure more formally that qualitative idea of treeness with a couple of different indicators, one of which is geometric, the other of which is purely topological. So the first, the length redundancy, just tells us what proportion of the total length in that city's network is in excess of that minimum spanning tree. And then the link redundancy is a purely topological measure akin to a normalized version of the circuit rank. And it just tells us what proportion of the edges or links in that network are in excess of the minimum spanning tree. Or in other words, how much needs to be removed to produce that minimum spanning tree. The math is very simple. The length redundancy is just the length of the tree divided by the length of the graph, subtracted from 1. And the link redundancy is just the number of edges minus the number of nodes plus the number of connected components, if there's more than one. And then we normalize it by the edge count to get that proportion. So they're both interpreted the same way, the proportion of stuff in excess of the minimum necessary to connect up the full network. So what I wanted to do for this project is compare street networks to some empirical baselines, that is looking at other kinds of networks in the world to understand to what extent street networks are similar to or different from them. So here you can see some treeness measures, specifically the link redundancy of some non-street networks that I was able to pull from the literature. So for example, the first one is the MSN Messenger network. It's a social network, totally non-spatial, and its link redundancy is 0.86. In other words, we'd interpret that as 86% of the links in that network are redundant. So you have a social network, lots of people who all know each other. 80% of those friendships are redundant in terms of being able to trace a path completely across the social graph. Our second one is a spatial network. So that's the European airline network. Spatial networks can be kind of weird because there's different ways to interpret it. In this case, for the European airline network, of course, the airports are spatially embedded nodes. The edges, so the flights that connect those airports to each other, don't follow a consistent spatial embedding, and it's non-planar. And so we see here that the treeness is 0.88. So about 88% of the flight paths in this network are redundant. There's another way that you can more minimally traverse the full graph. And then lastly, the Delhi bus route network is 0.64. So this is a more formal spatial network, more akin to a street network, but rather than infrastructure, about public transit routes. And we see that about 2/3 of those links are redundant. Okay, so if these are some empirical baselines for other kinds of networks, we can then look at street networks themselves. And for the link redundancy specifically, we see numbers like this. So we have a range from 0.03 to 0.45 across every urban area in the world. So here I looked at about 10,000 street networks. These are urban areas rather than municipalities or any other definition. And these definitions come from the global human settlement layer. But across those 10,000 urban areas that we've got, we see a range from 0.03 to 0.45, and the average, the mean city street network has a link redundancy of about 0.28. Okay, so what that means is that the average city, about 28% of the streets could be considered redundancies compared to that minimum tree to get across the whole graph. But the most interesting number to me here is the bottom one, the maximum. So the most redundant street network in the world is 0.45. And if we look back at the previous slide, we can see that compared to these empirical baselines of three easily accessible networks where I was able to find the numbers I needed from previously published papers, there is no street network anywhere in the world that even comes close to approaching their levels of redundancy, even the public transit network in a city. And that's interesting to me. And I think it tells us something about the nature of cities and their street networks. I'm going to be returning to a few times in the remainder of this talk. But to see what this looks like in practice, I want to briefly here first consider the treeness of some different megacities around the world. So here we're defining megacities as urban areas with at least 10 million people as residents for population. Bangkok has the lowest link redundancy, so the highest treeness of any of these megacities in the world. Buenos Aires has the highest redundancy and the lowest treeness. So here I just have five of them. I think in this data set there's maybe 30 or so megacities by this definition. Bangkok is 0.13, meaning 13% of its streets are redundant compared to that minimum spanning tree. We can kind of see why here. This figure on screen comes from a part of Bangkok on the kind of the western side of the city. And it really does look like the kind of paradigmatic tree. Um, the arterial roads have these branches that come off of them, that in turn have some branches coming off of them that end in dead ends. That is, there's very little redundancy to get from one point to another. There's really only one path that you have to follow through the network to be able to do it. If we instead compare Buenos Aires, which is the most redundant network among all megacities, it looks like this. So if you compare them, Bangkok, Buenos Aires, you can quickly see that Buenos Aires's grid offers a lot more redundancy to it. That is, if something goes wrong on one part of the network, there are many alternative routes that you can traverse throughout this mesh to be able to get from your origin to your destination. And other megacities fall between these two. So New York, another grid-like network, is 0.34. London, one of the less redundant networks, is 0.21. But they all kind of fall within this range, at least for very big cities, between 0.13 and 0.41. And before I do this, if we look at this here to motivate that next slide, if you look at this image of Buenos Aires or compare it to the image of Bangkok, you can start thinking a little bit about how this idea of treeness links to ideas of connectedness or choke points or griddedness, which we can test more formally here. On the left, we can see the two indicators of treeness or redundancy on the y-axis, so the length redundancy in blue, and the link redundancy or the normalized circuit rank in red. And then just looking at their statistical relationships with a few other urban characteristics. So on the left, we are measuring their relationships with the average node degree, which is an indicator of connectedness of the network. And we can see that more redundant networks are more connected. Conversely, more tree-like networks are less connected. Which makes sense. That's basically what we were seeing here in Buenos Aires. In the middle, we have the Gini coefficient of node betweenness centralities, which is a measure of how concentrated choke points are in the network. That is, the node betweenness centrality is a measure of the importance of individual nodes. If we take the Gini coefficient of those across a network, we can understand how concentrated they are into certain important parts of the network. For example, if there's a city that has two sides of the river and a bridge linking those two sides of the river, there's a lot of shortest paths that end up getting concentrated into that bridge. So it has a very high Gini coefficient here. What this center plot tells us is that More tree-like cities tend to be more prone to that high concentration into choke points, similar to what we saw in Bangkok. And then on the far right, we have a measure of circuity. In essence, it's the inefficiency of the infrastructure. So how much longer the actual links in the network are, the streets are, than shortest paths would be. So how much they diverge from from shortest straight line paths. And we can see here that more tree-like networks also tend to be more circuitous. But perhaps most interesting to me was the distribution of treeness across all these urban areas in the world. The first time that I saw this histogram, I was surprised to see it. And if we single out just the link redundancy here, so that normalized circuit rec, it looks like this. What surprised me about this histogram when I first saw it was that this doesn't look like the distribution of a lot of other urban form characteristics, or say city size around the world. This is very peaked. There's a strong characteristic central value. It has very thin tails, and there are essentially no outliers here. I'm going to talk about each of those characteristics in the next few minutes, a little bit more formally. But this doesn't look like a lot of other things that we measure when we measure urban form. And in particular, that idea of there not being any outliers here in this graph, I'll show you formally in a minute, but that's of particular interest to me because of that story of heterogeneity. Usually when we're talking about differences between places, we're thinking about what's unique about them, how they're different from anywhere else in the world, how a place like Venice is drastically different than a place like Phoenix. But at least according to this measure of treeness, there aren't any extreme outliers. So I want to take a few minutes here and think about that idea of heterogeneity to set up the last part of this talk around converging toward homogeneity. So typically, when we're thinking about differences between cities, we're talking about their heterogeneity. And I think we can see that really neatly here if we hold a bunch of different cities at the same scale and compare their street networks to each other. So those street networks really structure a lot of the urban form, the blocks, parcels, the buildings that exist inside of them. So here I'm holding 4 different cities, all at the same spatial scale of 1 square mile. And we can quickly pick out some of those differences between them. These street networks are shaped by different transportation technologies and design paradigms, different eras, different planning regimes, politics and expressions of power, local economic conditions and terrain. For example, if we think about the histories and values embedded in the classic street grid, such as in New York, but dating back to Hippodamus's early urban design work in ancient Greece, and the Spanish Law of the Indies, and the U.S. Homestead Act, and the New York Commissioner Plan. The grid has been used for millennia to express a certain sense of human order over the landscape, to make spaces more amenable to real estate speculation, economic development, or even to organize transportation around power and control. Conversely, if you think about the different histories and values that are embedded in Haussmann's renovation of Paris in the 19th century, or in different cities and suburbs around the world, such as US Sunbelt suburbs, and the notions of privilege and lifestyle and exclusion that are very explicitly built into the design of these different places in different parts of the world. If we start to add in building footprints, points of interest, amenities, land use, we can start to think about people's ability to access their daily living needs and how different that looks in different kinds of cities worldwide. In particular here, looking at the top at a couple of 19th century North American cities versus in the bottom, informal settlements in the global South with very different forms of formal circulation before informal circulation takes over in those informal settlements. And As an urban planner, one thing we often think about is how planning and technology reshape the urban form over time. For example, here we can see that heterogeneity over time with three different snapshots of US cities on the far left, kind of the classic deformed, imperfect grid from the early 20th century, in this case in Berkeley, California. In the center, kind of the early forays into designing around the automobile, in this case in the 1940s, where the street network remains relatively well connected, but block lengths have gotten longer, more curving, and more predicated on the idea of accessing urban space through the car rather than on foot. And then finally, kind of the culmination of automobility in the US at the very end of the 20th century, the disconnected dendritic suburbs of places like Phoenix, Las Vegas, and Houston, where the street network is very disconnected and shortest paths are very circuitous to get from you to your neighbor because you have to go all the way around the streets to get there. One way that I've measured this idea of griddedness and thought about its heterogeneity in particularly street network forms is through this idea of the entropy of your street network. So this is a visualization of that in New York, which is, kind of a clear case of it. So measuring the entropy of this, we can visualize with a polar histogram. So that polar histogram, it's like a regular histogram, only in this case, each of the bins represent 10 degrees around the face of the compass, and each of the bars' lengths represent the relative frequency of streets that point in that direction. So in Manhattan, you're predominantly on a grid, north, south, east, west, shifted off of true north by about 29 degrees. And that shows up in its polar histogram. There's a little bit of noise in parts of New York where the grid isn't perfect, and it shows up as noise around the center of the polar histogram. And we could formalize this measure through various measures of entropy. In this case, we could look at the Shannon entropy of those bearings to talk about to what extent the whole street network has streets pointing in the same directions as each other, or if they kind of point in all different directions. So comparing to New York, we could look at a place like Detroit, where we have two different grids here, and we can see them both in the polar histogram. So the older original grid is offset from true north and is aligned with the waterfront in Detroit. The later grid built around it comes from later parts of the 19th century after the US Homestead Act reorganized the rest of the city onto this grid, and it follows that instead. You can pick them both out in the histogram. If you take a city like Boston, you start to see higher entropy, so a more different kind of place. In Boston, you have a couple of grids in South Boston or in the Back Bay, but they don't align with each other, and they don't align with the rest of the city, which is a lot of older urban villages that agglomerated together over several centuries into Boston's higher entropy histogram of street bearings. So I've looked at this for several thousand cities around the world. Here are 100 of them from very low entropy cities, predominantly in North America at the top, going down this figure to high entropy urban street networks in Europe, Asia. One interesting exception in the very bottom right is Charlotte, North Carolina, the highest entropy urban street network that I found among large cities. Charlotte is like a big bowl of spaghetti in its entire city. The point of all of this is that we're able to tell this really clear story of heterogeneity by many measures. It's very clear how cities differ from each other, and most of our indicators are designed around telling that story of difference to try to explain downstream outcomes. So in this case, the navigability of the street network, or the ease of provisioning a transit system through it, or even spatial cognition and how entropy shapes your ability to spatially reason later in life based on what kind of environment you grew up in. But what I want to do for the remainder of my time this morning is shift away from that focus on heterogeneity to think about a different kind of story here, inspired by what I was looking at with treeness, where I was surprised to see that those treeness indicators tended to not show a lot of heterogeneity, but instead tended to have a really characteristic scale with very few outliers. So perhaps by certain measures, urban form, in this case, operationalized through street network form, could be a lot more homogeneous than we tend to think when we're talking about that story of differences to explain different outcomes. So I'm interested in this hypothesis of universality through this idea of universal patterns that exist in street network form. So to put it here, cities of very different origins, histories, and planning paradigms may converge onto a very narrow set of possible street network forms. That is, there are many possible cities that we could build that are technically feasible, that planners could create. They don't exist anywhere in the world, and instead we have converged through self-organization or through central planning onto a narrow set of that possible superset of urban forms. This is what I'll try to persuade you of for the last 15, 20 minutes of my talk. And I'll explain at the very end why I think that may be happening. First off, here's how I tried to test this idea. So first, I modeled all the street networks of the urban areas in the world, filtered by, say, large towns or bigger. So I'm cutting these all off at the street networks have to have at least 100 nodes in their network. So we're not looking at little villages here. So we've got about 6,000 urban areas. I calculated several indicators of street network form for each of them. And then I calculated several measures of statistical dispersion for each of those urban form indicators. And then based on those measures of dispersion, do we see heterogeneity? Do we see long tails, fat tail distributions? Or do we see a sort of convergence onto a very peaked histogram? So first off, those indicators of street network form. Treeness, we already saw from the beginning. That's what motivated this whole thing. We'll look at the link redundancy again here. The second one is circuity, which I talked about briefly earlier. It's how much longer the edges, the streets are, than straight line streets would be. The third indicator of form is the average node degree, which we saw briefly earlier. That's our measure of how connected the network is in terms of how many streets are there connected to each intersection or dead end, the nodes, on average. The fourth is that choke point indicator I talked about earlier. It's the Gini coefficient of node betweenness centralities. Just tells us to what extent the network relies heavily on its most important nodes. And then lastly, the average clustering coefficient, which tells us, like for an intersection, how much its neighbors tend to be neighbors of each other as well. So to what extent cliques are formed in the graph. I want to then compare those to a few baselines. I'm going to look at other urban indicators. So I'll look at the average elevation where the city was built, with the idea being that we tend to build places relatively close to sea level for historical reasons. Easier to build there, access to water, all kinds of stuff. So we'll look at its distribution. Second, the population's exposure to greenness, which I'm able to pull from the global human settlement layer. So, to what extent are the residents exposed to greenness in their city? And then a few different ways of trying to get at the size of the city. So its population, its built up area, and then a couple that superficially seem related to the street network, but are really just measures of city size. So how long the streets are, total street length in the city. And then lastly, the intersection count. So how many junction points are there across the city? And then for each of those indicators, I'm going to calculate those measures of dispersion to understand are places all kind of converged and similar around the world, or are they really spread out and very different around the world? So the first is the coefficient of variation, which is just the standard deviation over the mean. It just gives us a relative measure of how dispersed cities are. The second, and similar to that, is kurtosis. And in particular here, we'll look at the excess kurtosis of the distribution, which tells us about the tails. It's a measure of tailedness of the distribution, which tells us something about how extreme outliers are. So are there cities that are extreme outliers or not? The third and fourth are similar to each other. So the Gini coefficient and Shannon entropy respectively tell us about the inequality among the distribution's values or the uncertainty across the distribution. So are all of the cities very evenly distributed across the observations or are they not? And then lastly, and the one that's most interesting to me is a formal test of the presence of extreme outliers. So here I just use a very simple thing called Tukey fences at 3 times the interquartile range, which means that any city that is more than 3 times the interquartile range is going to be called an outlier. So do we see outliers or do we not? Okay, so I want to start here by showing you what heterogeneity looks like. These are my other urban indicators, measures of the elevation at which cities tend to be built, how exposed the population is to greenness, and then different lenses to look at how big the city is. Heterogeneity here looks like really long tails, power law distributions, log normal distributions. But the point is, on the far right of all of these histograms, you have these long tails that stretch out into the distance, where there are some cities that are very, very different than the bulk of cities, which are on the left, and you see most of the mass of these histograms. So for example, if you look in the very top left, population in millions of people, what this shows us is that most cities tend to be small, medium-sized cities. There are lots and lots of small and medium-sized cities all around the world, thousands of them, in fact. But there are also very few, very large cities in parts of the world. That long tail that stretches far off to the right, up to 30, 40 million people for places like Jakarta, Tokyo, Mexico City, Sao Paulo, Seoul. Some places are very, very large. So in other words, there isn't a characteristic scale for city size. You can have extremely small cities. You can have extremely large cities. You can have cities that are thousands or tens of thousands of times larger than other cities. That's the important takeaway here for heterogeneity. Places aren't necessarily that similar to each other. They can look drastically different. We see that for elevation as well on the bottom right, which is interesting. The elevation chart shows us that most cities are indeed built fairly close to sea level. That is, near the sea or along rivers that drain to the sea, but aren't thousands of meters above sea level. However, there are some cities on that far right tail that are built thousands of meters above sea level. Those cities around the world that are built high in the mountains. They're rare, but they exist. Again, this is our image of what heterogeneity looks like. Now, we can contrast that to our measures of street network form, which all look like this. They're very tight distributions around the mean. They have very thin tails. There's no tail dragging off to one side of the histogram here. And the way I've tried to show that is by these dotted lines that indicate for us where the min and max values are. That is, there's no city on one side of the histogram that we just can't see it because its bar is too short. In fact, those dotted lines show you the full range of the distribution. The dashed black line in the center shows you the mean value. And what I did for each of these x-axes is I constrained them to theoretical values. It's an arbitrary choice on my part, but let me explain a couple of them here for why they exist. For example, on the far left, we'll interpret average circuity. Average circuity's x-axis ranges from 0 to 1. A 1.0 for this measure would mean that the city's streets are twice as long, so twice as circuitous, as straight line streets would be. It's entirely plausible for planners or urban designers to build streets that are twice as circuitous as straight line distances. It's not efficient. It's not common sense. It may not be a good idea, but it's entirely possible. As you can see in this histogram, though, there's no city anywhere in the world that comes anywhere even close to that. The maximum value is around 30% more circuitous than straight line distances. Similarly, for the average node degree, an average node degree of 1 would mean that the city is predominantly dead ends. Average node degree of 6 would mean it's predominantly six-way intersections. It would be rare, but a place like Washington, D.C. has a grid with diagonal streets laid across it that cut the blocks into triangles instead of into squares or rectangles, and you end up with a lot of degree 6 intersections. But there's nowhere in the world that averages that, even though it's possible to have done so. That is, all of these street network characteristics in these histograms show us that only part of the possible parameter space has actually been explored by planners, perhaps for a variety of good reasons that I'm going to come to close in just a few minutes here. But the point is, these cities don't really show outliers, and they have very thin tails. And we can measure that everywhere in the world. So here, I've broken them out by geographical region. Previously, it was all lumped together. Here's by region. Each region of the world gets its own kernel density estimated distribution, just to show you that it's not like African cities are on one side of the histogram, North American cities are on the other. They all kind of sit in similar parts of the available range of values. Okay, last thing to show you here with numbers are those measures of statistical dispersion. And what I've done here, I've sorted each of the indicators from the most dispersed on the top to the least dispersed, so the most homogeneous on the bottom. And I've colored in orange all of our street network indicators so you can pick them out. And as you can see here, the street network indicators have sorted to the bottom. They are by far the most homogeneous, the least dispersed of all of these urban indicators. And in particular, if you look at, say, the coefficient of variation or the kurtosis here, you can see that many times street network form is several orders of magnitude less statistically dispersed than other indicators of city characteristics are. Same thing if we look at the uncertainty or the entropy, concentration across a distribution. Again, street network form tends to be the most homogeneous. And then lastly, the one that I mentioned earlier I was most interested in, this is the percent of urban areas that are extreme outliers by our definition earlier. You can see by city size, typically 7 to 8% are outliers. Those are the places like Tokyo, Mexico City, Jakarta, that are extremely large cities. Greenness, average elevation, about 4% of cities are outliers. But if you look at the bottom in orange, all of our street network form variables show either no or a trivial number of outliers. And in fact, 3 of them, treeness, the Gini coefficient of between the centralities and the average node degree, there are 0 outliers. There is no outlier anywhere in the world, which we don't see for other urban indicators. Okay, so I want to wrap this up for just a couple of final minutes here and think about what's going on. I want to first kind of interpret what that was looking like to me, and then secondly, try to explain why I think that might be happening. So first, what I see going on here. The short story is that the street network form measures of topology and geometry tend to be a lot more converged. They're a lot more homogeneous across all the cities in the world than those other urban indicators are. That is, you can see cities of any size, you can see cities of any elevation, but you can't find a city of any treeness, for example. Cities tend to be similar in terms of their treeness values. What that suggests to me is that urban street network form tends to be invariant to the underlying details and dynamics of the city system. That is, many different processes, different planning paradigms, different terrains, different economic conditions, different eras of development will all converge to generate these similar street network forms regardless of the underlying city type or era. That is, they're drastically different cities in terms of their size, in terms of the century in which they were built, but they still generate, on average, similar street network forms to one another. And on that note, I want to think briefly about why. Why do street networks look more similar to each other than cities seem to be? So first off, quasi-planarity. Urban street networks are quasi-planar graphs. That is, a planar graph is one that can be embedded on a two-dimensional plane without the edges crossing each other at points that aren't nodes. So cities are built basically on a planar-like surface of the Earth. Street networks are quasi-planar in that they're mostly planar, but they do still have some bridges, tunnels, overpasses, underpasses that occasionally break that planar constraint, but they're still mostly planar. And planarity constrains certain characteristics of a network, particularly topological characteristics like the average node degree, its ability to have small world properties. And I think we see that here. To explain this with an example, a social network in which you're not embedded in a plane, you could have dozens or hundreds of friendships. That is, the average node degree could be very high. People could have lots of connections to each other. In a street network, you can't see that. With intersections and streets embedded on the surface of the Earth, you're not going to find a city street network where you have 100 streets connected to each intersection. It's going to be typically something like 1, 2, 3, 4, maybe 5 or 6, but not much higher than that. Second, are urbanization processes themselves. Um, so Mark Bartholomew had an interesting paper about 10 years ago in which he showed that current arterial roads today could be traced back to original rural roads between villages before urbanization took place. That is, urbanization itself was this space-filling process that filled in around those original rural roads, turned them into an urban arterial backbone, and still concentrates between the centrality values on it to this day. That is, if urbanization itself fills in space around these important roads, you end up concentrating importance onto those roads as time goes on. And I think that explains a lot of what we're seeing with the concentration of Gini coefficients between the centralities, because we're just seeing how that process unfolds and naturally concentrates and continues returns to scale for already important links in the network. And that, I think, to some extent explains what we saw for treeness as well. But in particular, the last one, this idea of optimization, and the one I want to conclude on, I think explains a lot about redundancy, treeness, circuity, efficiency, and a lot of other things. That is, there's a reason why self-organized cities converge onto similar street network forms as centrally planned cities do as well. And that is, they both represent a certain optimality. If we take the treeness example, there are a lot of benefits to redundancy. Redundant networks are more prone to resilience when things go wrong. You have other routes that you can choose to take with more passive redundancy, but there are also drawbacks to redundancy. It's expensive. It's expensive upfront with capital costs to build a redundant link, and it's expensive on an ongoing basis with maintenance costs to continue to maintain more infrastructure than the minimum necessary to connect points in space to each other. So what I would argue is that cities show us a certain optimum. The fact that they all converge onto narrow ranges of values tell us that there are these certain approximate basins of attraction that cities end up in, whether self-organized or centrally planned, because they work well. That is, if city street networks exist to deliver functional transport, I think a lot of the street network forms that we're seeing exist consciously or subconsciously because they deliver relatively functional transport. So I will end on that note. Thank you all for attending, and I'm happy to answer any questions if there are any. Thank you.
Hi, Luca. I think we've met a million years ago at Birmingham University.
I don't know.
Hi, and thanks, Geoff, for this fascinating point of view and the underpinning research. I'm from Manchester today, from the Manchester School of Architecture. I have been thinking. Your presentation made me think a lot, which it's great, and you're talking about the entropy, which is also fascinating. And I've been thinking if through that lens you have been exploring any of the challenges that the tree approach might bring about and help us as urbanists. Um, I can't help but thinking that, the Hippodamian orthogonal planning is what's probably causing cities to be full of cars. And, how do you turn the entropy into a goal? I would think that, a tree in the more abstract approach would give a more organic reshape than the orthogonal planning, which could help us with some of the goals. So, what's your opinion of that? How do you bring about the challenges that could allow us to
Yeah,
progress?
yeah. No, this is a really good question. So a couple things. I guess I'll address the treeness of cities first. So treeness is cheap. It's good for resource constrained places because you have to build less stuff to be able to get through the network. But it's bad for efficiency, in that it makes you have to kind of route around in the network instead of being able to go in a straight line, which would be redundant links, right? Now, efficiency in modern cities often takes on these connotations of cars, right? Like cars are fast, you can get to your destination right away, and air conditioning in your car, it's wonderful. But in reality, I think efficiency really comes into play to benefit pedestrians and active modes of transportation because what you get with inefficient networks is artificially inflated shortest paths, which mean that it's hard. It's a much longer trip on foot, and those are the trips that start incentivizing people to take faster modes of travel. Maybe they'll bike it if they feel safe cycling. If it's a city where you're not safe cycling, maybe you say, I give up. I'm going to buy a car as soon as I can afford one, and it's one more person on the road who's sedentary and creating air pollution, and putting other cyclists at risk, on and on and on, right? So I think there are these second order effects of treeness beyond the first order effects of the benefits of redundancy and its resilience in the street network. I think there are these broader planning goals that end up getting implicated when we think about redundancy in terms of efficiency and how people do mode choices. Similar for entropy, there are a lot of benefits to building a grid-like city. Um, it's highly connected. It's a really easy way to make four-way intersections everywhere to give people many points of choice for how to percolate throughout the urban fabric around them, compared to three-way intersections or dead ends. It's very fast and easy in rapidly expanding places. Today in the global south, 100 years ago in North America. There are lots of reasons to do it, but it's not particularly good for spatial cognition. So studies have shown that growing up in grid-like environments is much harder for you to navigate complex environments than it is if you grew up in a more high entropy, spatially complex environment. So again, it's trade-offs. But at the end of the day, once you've built the urban form, it's roughly permanent. Old Roman patterns still exist throughout Europe, and cities are kind of built around those original backbones, because it's really hard to rebuild a city from whole cloth. Even if they burn down, places like Chicago, San Francisco, London still will have similar patterns to what they looked like before they burned down.
Brilliant.
Thank
Thank you
you.
so much.
All right. Okay. Thanks very much. Yeah, I mean, to some extent, Geoff, the elephant in the room on this sort of thing is relating to street networks is the potential dynamics of street networks because networks, of course, are built over periods of time in that sense. So let me give you an example. I mean, we in our group here a long time ago, 20 years or so ago, did a project on town centres, and we chose a town centre in the Midlands of Britain called Wolverhampton. to look at it. So we were looking at the street pattern and so on. And one of the features of this particular town, Wolverhampton, is that it's the only town in the UK, as far as we can gather, and I think this is pretty true, the only town in the UK that has a perfect ring road. In other words, there are ring roads which were built from the 50s, well, right, no, from the 30s onwards in British cities, but this one has a complete ring road. When we began to study it and to look at the town centre and the layout and so on, and the ring road, we also discovered that the road from central London to northwest Wales, which is a Roman road called Watling Street, that actually ran through the town centre. And so when we looked at this particular town, we didn't use any of the measures that you've been using and so on. And it begs the question we probably should be really looking at it because it's an interesting case. But the particular issue was that, in a way, in a very kind of casual way, there are at least three periods, if not more, which we can identify as the time over which the network was actually established. And so it'd be very interesting in terms of your a massive database in cities to be able to put a dynamic on it in that sense, to actually try and look at the different developments of networks in those cities and to see whether or not the various coefficients and so on, the various parameters that you've identified, statistics, actually vary with respect to the time when the networks were developed. So it's not so much a question. It's sort of, I suppose I'm saying, are you looking at dynamics? Because dynamics of networks is to some extent a very obvious thing to try and do. And I do appreciate the difficulty of doing this in terms of getting data historically in terms of the evolution of networks.
Yeah, Mike, thanks. No, I completely agree with you. I think the dynamics are the obvious next step. It's something that I haven't done yet because this is just the first part of this work. But yeah, that is the plan for the coming few months. Couple ways I've been thinking about it. One would just be from a single city change over time and to see how that growth process changes some of these indicators that I've been measuring. And then the second way would be trying to think about different places around the world from different eras. Can you find heterogeneity within those converged histograms? Are there different regimes within it that you can link up to older or newer places? I think probably yes. I can get roughly pretty good vintages for street network design in the United States. I don't know about other parts of the world, so if somebody does know, it could be a nice collaboration to look at that evolution question.
Mhm.
Well, thanks, first of all, Luca and Jeffrey, for the organization and the wonderful presentation. I was wondering whether we can also link this research on homogeneity and street networks in world cities with the theories that were developed at UCL by Bill Hillier and all the Space Syntax School. Things have moved a lot methodologically from the way they used to identify what they call foreground networks. But the idea is that maybe there is much more homogeneity in these foreground networks in world cities and more cultural specificities in the background networks. So, of course, the foreground networks apparently is not just the set of streets that concentrates the most between a centrality. It's a bit more sophisticated because we have to deal with heterogeneity in the network density. So we don't want to have a second or third tier street in the city center appear more important than first tier street in the outskirts. But once we are able to have a good method to detect this foreground network in a heterogeneous city, maybe this is the hypothesis that Heather had. There is much more homogeneity in the meshedness of these foreground networks than in the background networks, which can be much more culturally specific with tree-like structures in certain cultures in certain historic period, and more meshedness in other cultures and other historic periods. But we are talking about here the background network, not the foreground one, where your hypothesis could be even stronger.
That's an interesting point. And Giovanni, I need to compliment you on the beautiful urban form diagrams behind you on the wall there. We could pick out some nice street network designs out of that. Yeah, absolutely. And in fact, someone else recently mentioned to me when I gave a version of this talk that, or when they asked me what my hypothesis would be if we looked at, say, the dual graph, the line graph, instead of the primal graph. So like space syntax style, what I expect to still see the homogeneity that we see here, because the dual graph ends up being able to sidestep a lot of those constraints that a spatially embedded network, geographically spatially embedded, has. So I think maybe you would see more heterogeneity among them because of that. And to your point, I think it also opens up a really nice opportunity for looking at richer, more sophisticated measures of the city. Another good thing for to work on next. Thank you.
Yes, hello. Thanks, Geoff, for the very, very interesting talk. I'm Maarten, joining from Zurich, Switzerland. It's fascinating to think that all the cities are so basically homogeneous when it comes to the network structure of the roads. But I was wondering, have you ever also assessed, because even if you have a very narrow bandwidth of many of these network metrics, whether you've ever assessed the differences in the functionalities of these networks in terms of, for instance, number of traffic jams that occurred and things like that, or costs that the city spends on their transport. So more from a functional perspective, because I could imagine that even a small difference in redundancy already could have huge effects on traffic flows and things like that. So maybe in terms of functionality, the networks are actually very heterogeneous.
Yeah, Martin, this is a very good question. I have an unsatisfying answer of only kind of yes, but I'm hamstrung to some extent because those data are very hard to come by, at least internationally. So it's case study research, and you can do the case studies relatively well. You just need to work with someone in the city who can give you data on traffic jams, capital costs, maintenance costs, whatever. It's harder to do it globally. So for the kind of yes part, one thing that we do in my lab are simulations as experiments on different kinds of networks. So you take Phoenix, Arizona, and you take Rome, and you compare them to each other by simulating trips on them. One is high redundancy, one is lower redundancy. And then you break stuff on the network. So you say there's a bunch of traffic jams today, so you can't get through these points anymore. How does that affect trips? Whose trips are no longer completable? How much longer is the average trip? And then across enough of those networks, you can start to make some correlational claims about higher redundancy means this amount or this much less actual extra length when things go wrong on the network. So you can look at the functional performance of the graph. It's hard to do it empirically. It's relatively easy to do it with simulation. And I think case studies at this point, are most of what I've seen in the literature, or when I've done it myself, it's case studies to do it empirically.
Yeah, thanks.
Hello, hi. Nice to see you again, Luca, and it's just been such an interesting presentation. So thank you very much for that. I've really enjoyed it. And so my question is really about the prevalence and the increasing prevalence of cities now across the world being able to share best practice and having more of kind of a testing mentality, and then sharing those, and other cities maybe picking up design ideas and planning ideas, and what you think that information connectivity between cities, how you think that might play out as we maybe look to the future of what that might mean for our street networks.
Yeah, this is a great question. So the whole literature around like policy mobility how globalization causes policy circulation is really interesting. And I too have questioned to what extent that can help explain through best practices why there would be convergence onto certain forms. And I don't know. I think a lot of the cities that I'm looking at have evolved before the age of really circulating a lot of best practices or the kind of technocratic form of best practice planning, or even evolved independently in information vacuums through more self-organization than top-down planning. But all of that aside, we know that happens today. And especially with rapid urbanization in the global south, in the Middle East, or in China, we know what models they're following and what modernity looks like to rapidly urbanizing cities, for good or for bad, right? You know, if people want to drive in North American cities with cars everywhere because that's what the modern world looks like, you know, this can be a terrible thing. But a lot of that happens through policy mobility and through cultural hegemony. And it is this, you know, this homogenizing process. So maybe a good hypothesis would be 21st century cities would be even more homogenous than what we saw before, given globalism, you know, globalization of technology, planning theories, and so forth makes everybody do roughly the same thing as each other. Maybe there's even less local character than ever before. It's a good question.
Thank you. Yeah, that's my fear, I suppose, as well. But thank you very much.